Today we're going to be talking about parts per million. So parts per million is it's a formula that we're going to use, but what it's used for is it's used for expressing the concentrations that are very small. So normally we would just use molarity for concentration, and that's pretty much have been our go-to unit. But when the concentrations get really, really small, so let's say you were dealing with numbers that were like, 0.000001 molar. So that's a difficult number to write, even if you were to use it in scientific notation, 1 times 10 to the minus 6 molar, it just gets difficult. And they can be much smaller than that. They could go, to the 9 or even to the 12. So to the -9 and the -12. So they're used for really small numbers. And so we use parts per million because it's just more convenient. It's the same idea with atomic weights and grams. We could measure the weight of atoms in grams, but they're so ridiculously small that we'd have to use exponents in scientific notation every single time. So what they did was they just said, we're just going to call the weight of a proton 1, make a new system of weights, and that's going to make weighing atoms very, very simple. Well, the same thing pretty much happened here. They created a new scale when concentrations got really small. And so the same vocabulary applies: solute, solvent, solution. You can use any mass for this equation, so it doesn't have to be specifically grams or milligrams or anything like that, but the one requirement is the mass has to be the same unit. If they're not the same unit, then you're going to make a mistake. So for number 1, it says, a scientist wants to prepare a solution that has an active ingredient of 17 parts per million. So the way I write this out, I'm going to write 10 to the 6 out because 10 to the 6 is a million. So times 10 to the 6 is the same thing as saying times 10 to a million. So now the next step is the mass of the solution is going to be 2.5 times 10 to the 6 milligrams. So that many zeros. And they gave me 17 for my parts per million, and then this X is going to be in milligrams. So just be aware of that. The units of mass are going to be the same no matter what. So now for this one, I'm going to solve this one completely with you. So we distribute the 10 to the 6, so we get 17 equals a million X over that. Then you're going to make two fractions and cross multiply, and you get we get this. Then the last step is divide by a million on each side. And that's the active ingredient. Just so you're aware, 42.5 milligrams, that sounds like a lot, but a single extra strength Tylenol, if you're familiar with the size of that, that is 500 milligrams for a single extra strength Tylenol. So this is roughly 1/20th of what a single Tylenol would end up being in terms of its weight. So even this is a small number to work with. Like if you were a scientist and you had to weigh this out by hand, this is it's not impossible, it's just not, you're gonna have to pay really close attention to your weighing at this. It's not outside of the realm of possibility of what a scientist could weigh out, but it is a very small amount. Next one. A water sample is found to be contaminated with lead. The concentration of lead in the water is 800 parts per million. How many grams of solution will dissolve 6 grams of lead? So my 6 grams is my solute, it's the thing being dissolved, And my grams of solution is going to be the solvent. It's the thing doing the dissolving. Oh, wrong word. There we go. So for this one, I'm going to skip the work. Once you see it done once, you should be able to solve these for yourself. I'm going to go straight to the answer. So we end up getting 7,500 grams of solution. So that's, to put it in perspective, that would be about 7.5 liters of water. So about almost 4 2-liter soda bottles worth. Last one. Air contains a small amount of water vapor. Water in air, so now think about this, the water is in the air. So the water is what's being dissolved, and it's being dissolved in the air. Now, a lot of people don't think of that. We don't think of gases as being able to dissolve things, but they absolutely can. A gas can function as a solution the same way a liquid can, although in our world, it's almost always a liquid, but that doesn't mean air can't do it too. So they're just changing up the way they apply the word solution, but it still works here. The water in air is about 10 grams for every 1 kilogram. Be careful here because they just changed units on us. What is the concentration of water in air in parts per million? So in this case, I have 10 grams and 1 kilogram is 1,000 grams. I'm just going to convert. When we solve for this, we end up getting 10,000 parts per million, not PPP. I don't even know what that is. And there is all 3 problems. Also be aware, you may see this, I highly doubt it because it's not really listed, but all I have to do is change the last word, and if we wanted to measure something that was even less concentrated than parts per million, if you haven't figured it out yet, we could just change it to parts per billion instead of a million. And the only thing that would be different in the equation is it would be ppb here, and then instead of times a million, it would be times a billion. When things get really low in concentration, we can even change it to parts per trillion, ppt. So this would be a T here, and then this would be multiplied by 1,000,000,000. And you can keep going. There's no limit for this. You could even make them smaller and go parts per 1,000, which I believe on the practice problems, there is one of those. Parts per 1,000, but that's simple. It's just parts per 1,000, PPT. Again, I don't care about if someone were to say, well, how do you know the difference between trillion and 1,000? I don't care, whatever. You get the idea. Parts per 1,000, right? And then this would just be times 1,000 instead of times a million. So this concept can be adjusted to the concentration that you need to make the numbers basically easier for you to work with. Like, we like numbers that are like between, 0 and 100. We don't really like numbers that get too big or get too small, because then you have to start having exponents. In either case, that's what this is really good for.